Hello everyone, welcome back to another video. Today we are going to be using Python to create a model for the change in height of a fluid within a cylinder with respect to time. And before we hop into Python, we're going to be doing some equations up here on the whiteboard to solve for some equations that we can use within Python. And before we get into the equations, we'll go ahead and look at the setup for the problem. So we are going to have this cylinder here that has a height of 1 meter and a cross-sectional area of 1 meter squared. This is just going to be the area of the bottom circle right here. This is the cross-section and the area of that cross-section. And pretty much this cylinder is going to be filled to a height of 0.9 meters to start. And then eventually a hole is going to be plugged into the cylinder and fluid is going to start rushing out, right? And as that fluid starts rushing out at velocity v2, the fluid within it is going to start moving down at a velocity v1, right? And in order to model this, we're going to be using Bernoulli's equation to start because we're going to have this pressure within the cylinder of this gas, of this air that's at the top, right? Because the cylinder is only being filled to 0.9 meters, even though it has a height of 1 meter, which means there's going to be this air within the cylinder that's going to be at this initial pressure, which is 101,325 pascals right here. And as this fluid starts moving down and then out of the cylinder, the space that air has is going to be expanding, but the moles of gas isn't going to be changing. So that same number of moles of gas is going to have more room to spread out. So that pressure is going to be decreasing. And then we are also going to have that the area of this hole is going to be 0.001 meters squared. So we're going to be using that as well. And we also know that this pressure outside of the cylinder is going to be P2. That is going to be 101,325 pascals as well. And yeah, since we have all these P2s, P1s, and V2s and V1s, we can go ahead and use our Bernoulli equation over here. And we can go ahead and hop into that now. But before we do that, we are going to be using two situations to talk about. So situation one is going to be inside of the cylinder over here. This is going to be our P1 and our V1s. And then situation two is going to be outside the cylinder. Once it escapes through the cylinder, through the hole, and starts flowing outside of the cylinder, that is going to be position two. All right. And now we can go ahead and start talking about our variables up here. Obviously, you know, P2 is going to be 101,325, and that is not going to be changing. That is going to be constant throughout. And we know that P1 is going to be changing, right? Because it's going to start out at that 101,325 to start, but then it's going to start decreasing as the same moles of gas has more room to expand. So that is going to be changing. And then over here, we can say that V1 is going to be negligible for this problem because obviously this V2 is going to be much higher than this V1 because it's going to be a small hole with fluid moving fast through it. And comparatively, this V1 has a lot of space, so a big change in V2 is only going to be a small change in V1 due to the size of that hole. And we're also going to be squaring these numbers, so this small number is going to be even less compared to this big number that's also getting squared. So we're going to say that V1 is going to be 0 for this problem. And then for our positions over here, this would be change. This is change in position right here. We are going to say that our Z2 is going to be 0 down here at the bottom. And then our Z1 is going to be our initial height right here of 0.9 meters. And that is going to be changing with time too, right? As time moves on, more water flows out, and the height of that fluid is going to be going down. So our Z1 is going to be H, and our Z2 is going to be 0. And we are also going to say that our frictional heating is going to be 0 as well. So we can go ahead and write out all of these variables that we know. So we'll go ahead and do that now. So again, as we said earlier, P2 is not going to be changing. We know that's going to be 101,325 throughout the whole problem, no matter what's going on. But P1 is going to be changing as that fluid flows out of the cylinder, so we are going to need to leave that as a variable. And then again, over here, we can say that this is going to be a V2 squared over 2 once again, because we know that V1 is going to be negligible compared to V2 squared. So this is going to become just V2 squared over 2, like so. And then over here, we can say that this is just going to become minus GH, because we said Z2 is going to be 0. That's going to be our initial starting height at the bottom, and Z1 is going to be H. So this is just going to turn into G times negative H, otherwise known as minus GH. And this is all going to be equal to 0 because we said that frictional heating was going to be 0. And now we have three variables that are going to be changing. We have this pressure within the cylinder over here. We have this velocity of the fluid moving out of the cylinder. And then we have the height of the fluid within our cylinder. So those are going to be our three main variables right here. This is just the density of the fluid, which is going to be given to us. That's going to be a constant. That's not going to be changing at all. So what we're going to want to do now is we're going to bring in our ideal gas law to try and solve for this P1 right here. Excuse me. So with our ideal gas law, we know that PV is going to equal nRT. We'll go ahead and start writing this over here. And we can go ahead and solve for our moles. That is going to be within this pocket of air right here. So N is going to be equal to PV over RT. And this number of moles is going to be the same throughout the problem, right? Because there's going to be no air getting added into this air pocket, and there's going to be none leaving. So once we have solved for our moles of gas, it's just going to be remaining same throughout. And we know that our initial pressure right here is going to be 101,325. We are given that at the start. The initial pressure within this pocket of air is 101,325. And then for the volume right here, we know that it is going to be our cross-sectional area multiplied by this height right here, the height between where the top of the fluid level is and the top of the cylinder, which we can get by doing H minus HI, right? So we can say that this is going to be multiplied by AC, our cross-sectional area, and that is going to be multiplied by the difference between the height of the cylinder and the height of the fluid. So this is going to be H minus HI. And then this is going to be multiplied over RT. There you go. That is going to be our number of moles of gas within this air pocket. And now we can go ahead and move this over so we can solve for pressure, because that is what we're looking for. We are trying to get pressure. We'll do this down here. So P is going to be equal to nRT over V, like so. All right, and the next thing we're going to want to do is we are going to say that our volume down here, that is going to be equal to our cross-sectional. We already solved for this. We know that volume is going to be equal to our cross-sectional area multiplied by the difference in height of the cylinder minus the height of the fluid, H minus HI down here. And we can go ahead and plug this V in down here. We can plug this expression in for V, and we can plug this expression in for N right here. So we'll go ahead and do that. Alright, so we've gone ahead and gotten our N in here. Can't forget that RT. Alright, and then we're going to have our RT right here also over here. And then this is all going to be over our volume expression, which we have. All right, looking good. All right, and I did forget to mention that this volume right here, this is not going to be h minus the initial height. This is going to be the height of the cylinder minus our h as a function of time. So this is going to be our variable, however high the fluid is at a given time. So this is going to be decreasing as we move throughout. So we'll go ahead and label this as hx right here. This is not going to be the same as our hi right here. This hi should also be a little hi. So this hi, and then this is going to be hx, because this hi is just a constant right here. This is 0.9 meters, but this hx is not going to be 0.9 meters. It is going to be 0.9 to start, but that is going to be changing as the fluid level decreases. All right, and then we can go ahead and cancel some things out. These RTs are going to cancel, and then our ACHs are going to cancel. Not going to have to worry about those. And then we are pretty much just going to be left with, we'll go ahead and write it out. Actually, that's not true. Those aren't going to cancel. Our ACs are going to cancel. The H's aren't going to cancel. Go ahead and write that out. ACs are going to cancel. So our new pressure expression is going to be 101,325 H minus HI all over H minus HX right here. This is going to be our expression for our pressure that we can go ahead and use to plug in for P1. Okay, so now that we have solved an expression for P1, we can go ahead and substitute this in for P1 up here, and then try to get an expression for our V2. So we'll go ahead and substitute this in. Alright, and then this is all going to be over the density, and then we have everything else that we had over here. Minus GH equals 0. Alright, we can go ahead and erase this down here. Alrighty, so now what we can do is we can take out a 101,325 over the density over here, and that will give us a much simpler expression over here. So we'll factor out 101,325 over the density, and then this is going to become 1 over here, and that is going to be subtracted by h minus hi over h minus hx. 1 minus h minus hi over h minus hx. There we go, plus V2 squared over 2 minus GH equals 0. Alright, we'll go ahead and erase all this up here just to give ourselves a little bit of room. Start back up at the top. Alright, and on our next step, we are going to be wanting to get our V2 on one side and everything else over to the other side, because we are trying to isolate our V2 and get an expression in terms of V2. So we'll go ahead and add this over to the other side and then subtract this, which subtracting this, we can just flip the signs of our parentheses right here. So it become this minus this. So we'll go ahead and write that out. Like so, and then we can just go ahead and multiply this 2 over, and then square root everything, and that is going to give us our expression for V2. So this is all going to be getting square rooted, and then it's just going to be 2 multiplied by all this. And there you go. That is going to be our expression for V2 right here. Go ahead and erase this down here. All right, and the next thing we are going to be doing is we are going to want to solve. We are going to want to eventually get a differential equation relating our change in height to the change in time, because that is what we're going to be solving for ultimately in Python. We are going to be coming up with a model to show the change in height as the time changes. And the first way we can get to that is we are going to say that the change in volume within our cylinder as it relates to the change in time is just going to be the flow outwards going out of the cylinder. So we'll say that dV dt is going to be equal to negative Q out. That makes sense. Whatever is flowing out, that is ultimately going to be however much the volume is going to be changing in a negative manner, right? If you have, say, 5.5 meters squared that flows out, that is going to change the volume by negative 0.5 meters. So this expression here makes sense. And then we can say that the volume right here, this volume that we have, is going to be equal to the cross-sectional area of our cylinder multiplied by the height, right? Whatever that circle is multiplied by the height, that makes sense. That is going to be our volume right there. So we can say that the differential change in volume is just going to be our ACDH. And I guess we should say that this is going to be little h, since we don't really care a whole lot about the extra air at the top. We are only going to be looking at, this is just the volume of the fluid, so we are only caring about the height of the fluid, so this is going to be little h. And then our differential volume is just going to be ACDH. So dV equals ACDH, like so. And then we can say that our flow out is going to be the area of the hole in which the fluid is flowing out multiplied by the velocity, which is going to be V2. So we can say that Q out is going to be equal to our AH, which is our 0.001 meters that we said earlier. This is the area of the hole. And then this is multiplied by V2, the velocity of the fluid exiting the hole. All right, and then we can go ahead and substitute our ACDH in for our dV, and then our AHV2 in for our Q out. So this is going to turn into ACDH dt equals negative AH V2. All right, and then we can just go ahead and divide our AC over, so we get dH dt over here by itself. We'll get dH dt is equal to the negative product of the area of the hole multiplied by the velocity exiting all over the area of the cylinder. And there you have it. This is going to be our expression. This is going to be our differential expression that we're going to be using to solve for in Python and model using some graphing tools. And we'll go ahead and jump into that part of the video now. Alright, so we're going to go ahead and jump into Python now, and we've already imported the different functions that we're going to be using to create our plot showing the height in the fluid as it changes with time. We have imported our solve IVP, which is actually going to be solving the integral for the differential equation that we created earlier. And we have the make subplots function, which we're going to be using to actually create our plot. I've also gone ahead and added in all of our constants over here that we were given at the start of the problem. We have the height of the container, which was 1 meter, the initial height of the fluid, which was 0.9. Then we've got our cross-sectional area of the container, and then the area of the hole that's going to be punctured into the container. Then we've got the P external, which was 101,325 pascals. We've got our acceleration due to gravity, the density of the fluid, which in this case is going to be water, so this is going to be 1,000 kilograms per meter cubed. And then we have our Tn, which is going to be 10 seconds. This is just going to be telling our function when to stop running. And the first thing we're going to do is we are going to define a right-hand side function over here using time and y as our variables right here. And pretty much this is just going to be defining our differential equation, our differential height as it relates to the differential change in time function that we solved for earlier. So this is going to be returning that function, which I believe was the negative area of the hole multiplied by V2, which was the velocity of the fluid exiting the container, and then this was divided by the cross-sectional area of the container right here. Alrighty, and the next thing we're going to need to do is we're going to need to include our equation that we used to solve for V2 that we solved for earlier on the whiteboard. So I'll go ahead and get that written out here, and we'll cut to that so you guys don't have to sit here and watch through all that. Alright, so we've gone ahead and written out our function for the velocity, and now we are going to need to give a value for our h over here, because remember we had the height of our container as big H, and then the initial height of the fluid as hi, our 0.9 meters right here. But this h right here is actually going to be the height of the fluid as it's changing with time. That is not going to be a constant thing. That is going to be changing. So we are going to need to set this equal to y and then an array of 0 just to get a value for that. Alright, this function is looking good to go, looking smooth. Alright, and then next thing we're going to need to do is we're going to be doing our solve IVP function so that we can actually solve this integral right here. So we're going to say that the result is equal to solve IVP, and then this is going to be our right hand side, and then this is going to be running from 0 to Tn, which is 10 seconds over here. Alright, and then we are going to be doing Redao. This is going to be using the Redao method to solve, so we need to type that in. Alright, and then our dense output is going to be equal to true. We want this to have a dense output. Alright, let's see what this is looking like. Alright, so we have a few mistakes that we have made so far. First of all, we are going to need to include an initial height for this function to run through as a starting value, so we need to include an hi over here. And then another mistake we made is we need to include a -1 over here between these parentheses in order for this function to be run correctly. So we'll go ahead and run through everything, see how everything is looking. Alright, and it is saying that array must not contain infinites or NaNs. And pretty much what's going on here is we are getting negative values within our square root right here. And you know, obviously you can't square root something that's negative, so it's not functioning properly. So what we can go ahead and do is include an absolute function value. So we'll go ahead and do that. We'll put everything in absolute values, see if that corrects this issue that we're having, and it does. Alright, so now what we're going to want to do is we are going to want to go ahead and graph this out, see what it's looking like right now. So we'll go ahead and create a t-plot with a linspace function to give us evenly separated values from 0 to our tn. This is going to be our values that are going to be plotted on the x-axis. So we'll go like that. Alright, and now we will go fig equals make subplots so that we actually get our plots created. Alright, and then we are going to add a scatter to the fig. And our x-axis is going to be our t-plot, which we created earlier. So x is going to equal the t-plot. And then y is going to be equal to our solution of our res function using our t-plot values to solve the function. And then we are going to need an array value here, so we'll go 0. Let's see what this is looking like. Alright, as you can see here, it looks like the fluid is starting to leave this container here, and then eventually the velocity gets down to 0, so the fluid is no longer leaving. But then it starts going down again, which, you know, is not really what we want to see here. We want this to we want our graph to end at the time value when the velocity reaches 0. That is going to signify the end of our graph and of this expression over here. So we are going to need to find a way to get to find a value for when the velocity is going to equal 0 and have our graph terminate at that time value. And we'll jump into that now. Alright, so in order to get our graph to end at 0, we are going to use a terminal function. And in order to do that, it's pretty much going to look the exact same as this function that we already created over here. A few things are going to be changing. We'll go ahead and rename this function to v2 is 0, because that's what the purpose of this is going to be. Alright, and then pretty much this is going to be the exact same, except we are going to be returning our v2 over here. So we can go ahead and copy and paste this, and we're not going to need the square root or the absolute value function over here, because this is going to be returning it when it's 0, and obviously the square root of 0 is going to be 0, so we're not going to need all that. So we'll go ahead and copy this in here to the return. Hopefully I selected the right amount of parentheses to include. Alright. Looking good, and then we can go ahead and delete this line from the code, and then that should be it. Alright, and then we're going to do v2 is 0, and then dot terminal, and that is going to be put as true. Let's see if that's working for us. Alright, it is. Alright, and then we're going to go ahead and we are going to say that events is going to be equal to v2 is 0. So that knows to take into account this graph over here and when it is going to be terminating. So we'll go ahead and run that. Have no effect on chosen solver. Maybe it's just event. Oh, I spelled it with an M. Events. Here we go. Alright, that's looking good. Let's see what our new plot is looking like. Alright, as you can see here, it's still looking a little funny, and that is because our graph is still going from 0 to t end right here. So we're going to have to figure out a way to pull out the value for when the velocity is actually reading 0, the time value, and get this to end right here. So we'll go ahead and do that now. Alright, so we're going to go ahead and create a variable to signify the new endpoint for when the velocity is going to be 0, and we're going to call that endpoint. And this is going to be, in order to find that, we're going to do res.tEvents, and then we're going to have to pull out a value from an array within an array, so we're going to go 0, 0, like so. And that should give us our endpoint, the time value for when that velocity is going to be equal to 0. And then we can set our linspace from 0 to endpoint. And we'll see what this graph is looking like. And there you have it. This is looking good right here. This is what it is supposed to be looking like. As you can see here, after about a little more than 4.5 seconds, that velocity is going to be dropping off to 0. So that fluid is no longer going to be coming out. And over that a little more than 4.5 seconds, it looks like the fluid level dropped about a centimeter here, going from 0.9 meters to 0.89 meters. And yeah, there you have it. That is going to do it for today's video. Make sure to subscribe to the channel if you guys enjoyed and want to see more content similar to this. Leave a like on the video if you enjoyed, and have a good one.